So in this video, we are going to be going over PM1 and PM2 questions all in one, because there's not really a particular type of topic that's only asked in PM1 or PM2. Okay, we have a mixture. And you're going to go through this, and I'm going to pretend to be a student getting help. So I'm going to try to ask, typical student style questions, things that will be questions that might be on the minds of other students who are trying to learn this. All right, so let's go. Let's take it away.
Right, so question 12, you can see there's two parts to this question. The main part of the question, of the topic, is obviously to do with a differential equation. You can see that you have dh dt here. So we have to solve this differential equation. And with regards to solving differential equations, you have to integrate. Sometimes it's either an easy integration, but when it's a difficult one, you will have a part A to the question where you actually do the integration beforehand. So even if you can't perform the integration, they give you a form of the answer which you can then apply to the second part. And even though you may not get the correct answer or the correct values, you will get method mark for applying that question through the next part, the stage of the question. So let's have a look at question A. We can see that we have to integrate the product of two functions. So what's the rule that we apply for integrating the product of two functions?
Is it the product rule?
If it was differentiation, then yes, we differentiate with the product rule. But in this case, we're doing the reverse of differentiation,
which is integrated.
Exactly. So what's the reverse of the product rule?
Integration by parts.
There we go. Another tip is, if you're going to use a formula, formulas are provided in the formula booklet, but I always say copy the formula out, because the more you use the formula and write it out, you can see any twists and turns that you may have to apply. Right. So integration by parts. So the integration of u v dash is equal to uv minus the integration of u dash v. That's the formula. So if we look at the function, if we call the x as u, and our sine kx would be our v dash. So normally, if you have powers of x's in your expression, you make that u, unless you have ln, then that becomes a u. So here there's no ln, so u is going to be our x. So on the side,
so you're saying that if you have an ln, it's better to make the ln u because it's easier to differentiate ln,
exactly,
rather than integrating ln.
Exactly. Gotcha. So u becomes ln, if you have an ln. Otherwise, it's a power of x. So u equals to x. So u dash equals to 1. V dash equals to sine of kx. And we need to work out v. To get v, we integrate. So what differentiates into a sine is cos kx. And a common mistake is that you may get the sign wrong. So just ask yourself, like, if we were to differentiate cos, do you get positive sign or negative sign?
Get negative.
You get negative. And because our sign is positive, we need to balance it off by a negative. And when you differentiate, you multiply by k. Here we're integrating, so it's going to be 1 over k. Do the reverse. That's our v. We now just substitute that into the formula for by parts. So it's u times v. So we'll take our u and we take our v and multiply them together. So if you prefer, you can just write them out separately and then simplify on the next stage. So we x times 1 over k and minus 1 over k times cos of kx. That's our u times v, minus the integration of u dash, which is 1, times by v, which is minus 1 over k times cos of kx. Now, let's simplify this before we finish this part off. So we've got the x times everything inside the bracket, so that's the same as minus 1 over k times x cos of kx. The 1 obviously doesn't do anything. The minus 1 over k, we're going to pull that out, put it outside the integration, and there's two minuses which become a plus. So you get 1 over k integration of cos kx. Now, some people will probably leave the coefficients inside the integral and try to integrate that. So we take out the constant to make the integration easier. So if you now look here, there's no coefficients in the way. It's easier now to integrate the cos. Just like how we integrated the sine here without any coefficient, similar way we can do that. So what differentiates into a cos? It's sine kx. A sine differentiate into a positive cos or negative cos? Positive cos. Therefore, our sine will be positive. because our cos is positive. And so it'll be 1 over k sine kx because it's the reverse of.
What about plus c? Do we need to do a plus c here?
Yes, there is a plus c, but I was going to do that on the final line. I mean, you can put a plus c here, or you can put a plus c at the end. Now it's to just put all of them together. So we have minus 1 over kx cos of kx. And if you can now see that we have the 1 over k times by another 1 over k, which gives us 1 over
K squared.
K squared, and then sine of kx plus c. There you go. And if we now compare this to what we have here, it's the same expression, it's just swapped around. Yeah. Right. So if we just rewrite this as 1 over k squared sine kx minus 1 over k cos kx plus c, that matches the answer that we have here. Right. So part B. A theme park ride lasts for 70 seconds. And you can see that from the domain given, you can see that the maximum time allowed is 70 seconds, hence why it lasts for 70 seconds. The height above the ground is capital H. It's modeled by this differential equation. So the rate of change of height, or how fast the height is changing, is basically modeled by this fraction here. T is the time in seconds after the start of the ride, given that the passenger is 5 meters above the ground at the start. This bit here is giving you a condition here for your differential equation. When you get a sentence like this, what I always do is I just write down the pair of values that they give us here. So the passenger is 5 meters above the ground, means h is equal to 5 at the start of the ride, which means t equals to 0. So when t is 0, h equals to 5. Using this, we can actually work out any constant. So we can substitute that in to an equation that we have unknowns with to work out any missing parts. Okay, so to solve the differential equation, we separate the variables. On the left side, because we have dh on the top, we need all the h's on the left side.
So we'll move the 10h onto that side by multiplying.
And t's on the right side.
We're going to do the dt on the other side by multiplying.
Exactly. And just to keep in mind, only separate the variables once you have single fraction on either side, and we only use multiplication or division to separate the variables.
So we can't add or minus anything onto one side.
Only to get your single fractions on either side, where everything within the fractions are either multiplying or dividing. Once you achieve that, then use either multiplication or division to then separate the variables. So in this case, we don't need to add or subtract anything because we already have single fraction on either side, and everything within those fractions are either multiplying or dividing. So we can go ahead and separate them. To move the h, we can either move the h on its own, or we can move the 10h with it. Sometimes in questions where you have part A to the question, the 10, you can look from the format of the integration you've done in part A to see whether or not you take the 10 with the h or leave it behind. If we go back up and look at the integration, you can see that there's no 10 here. For that reason, we're going to take that 10 and the h to the other side and multiply. So we'll have 10h dh by dt equals to t times sine of pi t over 5. And then we need to multiply by dt on the other side. So we have 10h dh equals to t sine of pi t over 5 times dt. The variables are now separated, which means we can now put the integration signs in. Now, if we now look at this bit, and well, let me copy and paste the answer from part A, and then we can compare them. Right, so from part A, we saw that the integration of x sine kx gave us this answer here. Now, if we now compare this to what we have here, in order to use this answer within the next part of the question, we need to make the comparison between the two and make the link. So to make this the same as this, we're basically saying that x is t, And if you look at what's inside the sign, we have kx. So kx is basically pi t over 5, which means if we already know that x is t, so this implies that k is basically pi over 5. So just in case you're wondering where I got this from, or even where I got the x equals t from, if you look at this integration here, we can see that we have x times sine kx. If you look here, we have t times sine of whatever's inside the bracket. So if you compare them, it means x must be the same as t. So x equals t. And what we have inside the sign, which is kx here, and we have pi t over 5 here, those must be the same. So I've wrote down kx equals to pi t over 5. And given that x equals t, so the t and the x cancel off because they're equal to each other, we get k therefore is pi by 5. Making that change, we can now replace this with this. That's basically the answer to the integration, and put it here. So we have 1 over k squared, but remember k is now pi over 5. So we can write this as 1 over pi over 5 squared times by sine of kx, which is basically pi t over 5, minus 1 over k again, so 1 over pi over 5 times by x, which is t in this case, times by cos of kx, that's pi t over 5, and then plus c. Now we need to simplify this because this is too messy here. We have a fraction over another fraction. When you square a fraction, obviously you square both the top and bottom. So we have 1 over pi squared over 25. But if we now multiply top and bottom by 25, that 25 from underneath will just cancel off. So this will just become 25 over pi squared. We'll just do the reciprocal of a fraction. The fraction flips, the denominator goes to the top, and bottom pi squared stays underneath. And then we have our sine of pi t over 5 minus 1 over a fraction again, so the reciprocal of pi by 5 is 5 over pi, t cos of pi t over 5 plus c. So that's the right hand side of the integration done. On the left hand side, if you look at the left hand side, it's just integration of 10h with respect to h. It's just a year 1 integration here, so h to the power of 2 and divided by 2. So on the left hand side, get 10h to the power of 2 divided by 2, which just simplifies to 5h squared.
Should you do another plus c on the left hand side as well?
Okay, good question. So when we integrate, we do have a plus a constant. We have got a plus constant on the right side. We can have a plus a constant on the left side. But the thing is, there's no need to have 2 different constants because a constant overall at the end is still a constant. So even if
do one time,
just do on one side, and they say that it's the constant on the other side, but across, and the overall constant you get is that plus c at the end. So there's no need to put plus c on both sides.
Okay, but what if a student says, for example, that plus c belongs on this side with plus c, and this side is the plus c, and then they say, okay, I'm bringing the constant over to the other side, so I'm minus c to the other side, and then they lose c altogether. What would you say about that then?
In that, I mean, if you make that kind of mistake, then use different. Think of constants that being 2 different values. So different values mean different letters. So if you're going to use plus constant on both sides, maybe call one C1 or call C2, or use C and K, or C and D, for example.
On that side, we C minus K.
Yeah.
If you do that. So it's still a constant.
Still a constant.
C minus K. And that's why, to do away with all that,
just do plus C on one side, and that's it. You can't make that mistake. Right, so that's the first. So now that we have integrated, and from integration we get a plus C, we now have to figure out how to work out what that C is. This is where that condition they gave us comes in. So from this sentence here, the passenger is 5 meters above the ground at the start of the study. This is the information we take from that. So h is 5 when t is 0. So if we now write h equals 5 when t equals to 0, we will substitute this into our expression above. So that's 5 times by h squared. So 5 squared equals to 25 over pi squared times sine of pi times 0 over 5 minus 5 over pi times 0 cos of pi times by 0 over 5 plus c. Now from the substitution, you can clearly see that here sine of anything multiplied by 0 is 0, sine of 0 is 0, so the whole thing goes away. So this whole term is 0. Here you're multiplying by 0, so the whole thing here would be 0. So basically c would be 5 times 5 squared, which is 125. So c equals to 125, which means we can now rewrite this as 5h squared equals to 25 over pi squared sine of pi t over 5 minus t cos, and plus c, which is 125. So that's like the solution done for the differential equation. Because if you look at the next part of the question, the reason we had to solve the equation is because now we can find the height at any specific time. And here we need to find what the height is at 52 seconds after the start of the ride. So all we have to do now is substitute in t equals 52 into the formula. So 5 times h squared equals, if you substitute in t as 52 into the expression on the right hand side, you can either do them in parts or as a whole in one go. All right, so we get 56.702 dot dot dot. So divided by 5, we get 11.34, and then square root h equals to 3.37 to 3 significant figures. So that's in meters. Right, let's check the answer for this.
In the back of the book, the answer wasn't 3.37.
Okay, so either we've gone wrong in our calculation, or maybe substituting
I've checked
into.
the calculation, it's all good.
Or have you checked that if you're in radian mode?
Oh, actually. Oh, my calculator's in degree mode.
Common mistake. Always, yeah.
How would I
Always.
have known that this was a radian question then?
When it comes to integration, unless said otherwise, always assume that integration is going to be done in radians. It's always going to be in radians.
Yeah, same for differentiation too?
Yes, always in radians. Unless, say, if you see within the working out, you see a little circle meaning degrees, then
even the range is given in degrees.
Then use degrees. Otherwise,
so I'm gonna have to do
but when it comes to differentiation, integration is always in radians.
I mean, in an exam, if I had done this, if people had done this, and they've given this answer, they'd lose some of the marks, right?
They will lose the answer mark, but they will get their method mark.
Okay, right. Let's delete that answer. Just put a cross through it.
Okay.
Let's do the calculation again in radian mode.
Right. So this is wrong. So this is meant to be. So that's 101.83 dot dot dot, and divided by 5. 20.36, and then square root 4.51 meters. And I believe that's the correct answer.
Right, on to the next question.
But it's nice and it looks nice and simple enough. You got like a small expression given here, but 5 marks. There must be some trick to this. Well, it does say second derivative, so we have to differentiate twice. And x and y are on both sides, or even within the mixed up within the equation. So we have to differentiate using
implicit.
Yeah, good, because we have x and y's on one side. Common mistake is when people differentiate using implicit, they always forget to put a dy dx when they differentiate the y. So that's one thing we need to keep in mind. So let's start by differentiating the y squared. So y squared becomes 2y times by
dy over dx.
dy dx minus differentiation of x squared as normal. 2x, and differentiate the 8 gives you 0. And rearrange that to make dy dx the subject. So dy
Why are we rearranging for dy by dx?
So then we can do the second derivative. So dy dx equals to 2x over 2y, which we can now simplify as x over y. Now, technically, we can actually perform the differentiation in its current form like this. So the way it is, we can actually do another set of differentiation. But if you do it like this, you can see that you're going to have to use the product rule here, and then obviously differentiate this one separately. Now we can just use the quotient rule and differentiate x over y. So again, look up the formula for quotient rule. The derivative of u over v is u dash v minus u v dash over v squared. So here, so u is equal to x, so u dash equals to 1, and v equals to y. So what's v dash equal to? Dy dx. Now, when you differentiate the left-hand side, the left-hand side is already dy dx. So when we differentiate the second time, this will become d2y by dx squared. And on the right side, we're just going to apply the quotient rule. So you need u dash times v. So u dash is 1 and v is y. So that's 1 times y is just y, minus uv dash. So that's u and that's v dash. If you multiply those together, we'll just get x times dy by dx all over v squared. So v is equal to y. So v squared in this case would be y squared, and that's dy dx. So if you now look at this and look at this, can you see that we achieved that second derivative on the left side, but the right side is entirely in terms of y, but here we have x and y's in it. Okay, this is where we have to look at the dy dx and say, okay, is there a way we can replace this dy dx? Is there any way in the working out that we have dy dx? There you go. We can, well, not this one, we use this one and substitute in for dy dx and then simplify. And that should hopefully give us the answer. So we have y minus x times dy dx, which replaces into x over y all over y squared. And if we now simplify this, this is equal to y minus x squared over y all over y squared. If you want to get rid of the y from this fraction here, we're going to multiply everything on the top by y, and to balance it, we're going to multiply the bottom by y as well. So this now gives us y squared minus x squared over y to the power of 3. And that's d2y by dx squared. And if you note what we had initially at the start, y squared minus x squared is equal to 8. There you go. So this must be 8. So that gives you 8 over y cubed, and we have the expression. Double angles, right? So I can see because there's 2 theta double angles there. So we need to use double angle identities for this one. If you look at the answer given here, the right side has a single angle, whereas the left side is double angle. So before we even start, just try to recall the double angle formulas. Just write them all down.
So cos has 3 of them. How would I know which one to use?
I'll just write all of them out.
Okay.
Just download everything from your head onto your paper. So we have the double angle for sine. So sine 2 theta equals to 2 sine theta cos theta. Cos 2 theta, the default version is cos squared theta minus sine squared theta. And if we replace the cos squared with 1 minus sine squared, we get 1 minus 2 sine squared theta. And if we replace the sine squared with 1 minus cos squared, we get the third version, which is 2 cos squared theta minus 1. They're all equal to cos theta. So that's our double angle formulas. Now, if we now start with the message side of the expression given, which is obviously the left-hand side here, we're going to write 1 minus cos 2 theta over sine squared 2 theta, but I'm going to write this as sine 2 theta bracket squared. Avoid writing the right hand side within your working out, because you might be tempted to mix them all together, but aim is to show that this turns into the right hand side. So first thing we're going to do is we're going to switch the cos to theta. Now there's two versions for the cos to theta, so three versions for cos to theta, as I just said. To use the correct version, this is where you can have a look at the right hand side and see what we need to achieve. So sec squared is basically 1 over cos squared theta. Which one do we pick for the top? Well, I'm going to come back to the top, but the denominator is only one version, so let's use that first, see what we get. So it's 2 sine theta cos theta is our sine 2 theta bracket squared. You can now see that we're going to have sine squared cos squared underneath, and so if you look here, obviously we're going to have sine squared cos squared, but in the answer there's only cos squared on the denominator, so the sine squared has disappeared. So in order for the sine squared to disappear, the top must have a sine squared for it to cancel off. So that's a hint that the top therefore has to be the sine version of cos double angle. So we're going to use the double angle of 1 minus 2 sine squared for the cos. So here we're going to have 1 minus bracket 1 minus 2 sine squared theta. So expand the bracket on the top is 1 minus 1, and 2 minus becomes a plus 2 sine squared theta. The denominator would be 4 sine squared cos squared theta. You can see here the 1 and the minus 1 cancels off, and then we have the sine squared, which will cancel off this sine squared here. So this will leave us with 2 over 4 cos squared theta, and 2 over 4 is the same as a half, so 1 over 2 cos squared theta. So this we can split up as 1 over 2 multiplied by 1 over cos squared, and 1 over cos squared obviously is sec squared, so that gives us a half sec squared theta. So therefore we have k as a half. Now second part, hence solve this equation, must be linked to part A. If we look at part A, we can see that 1 minus cos 2 theta, 1 minus cos 2x. So basically x is the same as theta. So if you make the link with this and this one, we're saying that theta is the same as x. In which case, the expression we got here can be switched into this one here. So this equation here, we can just say this side is going to be the same as k, which is a half, times sec squared of x. So let's write this out. So question B, a half of sec squared x equals to bracket 1 plus 2 tan x squared. Expand the bracket, 1 plus 4 tan x plus 4 tan squared of x. And we have a half sec squared x here. So when it comes to trig equations, we don't want to have different trigs. So we need to now find an identity that replaces the sec squared with a tan squared. So if we recall the identity, 1 plus tan squared equals to sec squared x. So we have a half of 1 plus tan squared equals to 1 plus 4 tan x plus 4 tan squared x. I don't like the half there, so just multiply everything by 2 to get rid of that half. So we have 1 plus tan squared equals to 2 plus 8 tan x plus 8 tan squared x, and then move everything to the other side and simplify. So that gives us 7 tan squared x plus 8 tan x plus 1 equals to 0. And if you now just use the quadratic formula or your calculator to get the solutions to this quadratic equation, you would get tan x equals to two values. So one of them minus 1 over 7, and the second one is minus 1. Right, so we are solving the equation between minus pi by 2 and pi by 2. Let's just write this out on the side. So minus pi by 2 x pi by 2. Right, so it's a nice range because it's just between minus 90 and 90 degrees. So if we have the cast diagram written out, we're just basically looking for solution in those two quadrants. Angle here goes up to positive pi by 2, and this will go down to negative pi by 2. So in this region, the only place where tan is negative is where cos is. So this is the only solution that we're going to be looking for. So when we do tan inverse on minus 1 over 7, again, make sure that you are in radian mode. Right, we get x equals to minus 0.142 to 3SF, and the second one is minus pi by 4, which both of them are within range. You might be asking, what about the other solution? So the other place tan is negative is where sine is, but here it's beyond the range, so we can ignore the second solution. So these are the only two solutions to this equation. The vertical speed v of a skydive at t seconds after the parachute opened is modeled by this equation given here. So v equals to a plus b e to the power of minus 0.5 times t, where a and b are constants to be determined. Now we're given two bullet points to help us to work out the values of a and b. So the first bullet point tells us that the speed is 56 at the instant the parachute is open. So that means that when t equals to 0, v has to equal to 56. So the second bullet point gives us the speed 5 seconds after the parachute opens. So when t equals to 5, v equals to 10. So if you first substitute the first set of values in, so when t equals to 0, v equals to 56 into the formula, we get 56 equals to a plus b. E to the power of minus 0.5 times 0 is just 0. E to the power of 0 is 1, so that's just go away. We can just take that away. As 1 times anything doesn't really do anything, so we just get 56 equals to a plus b. If we now substitute in t equals 5, v equals to 10 into the equation, we get 10 equals to a plus b e to the power of minus 0.5 times 5, which is equal to minus 2.5. If we now solve this equation simultaneously, so we can subtract the bottom equation from the top equation. By subtracting, we get 56 minus 10 is 46. A subtract a cancels off, and then we have b minus b e to the power of minus 2.5. So factorize the b out. So 1 minus e to the power of minus 2.5. So therefore b would be equal to 46 divided by 1 minus e to the power of minus 2.5. We get 50.113 ... So we want to round that to 3SF, which is equal to 50.123 significant figures. Now to work out the value of a, we can just substitute this back into the first equation. So a would be equal to 56 minus b. So if we do that, so 56 minus the answer to the previous one gives us 5.89 if we round that to 3 significant figures. Right, so now that we have obtained values of a and b, we can now finalize the equation. So therefore the complete equation of the model v equals to a, which is 5.89, plus b, which is 50.1, times by e to the power of minus 0.55t. For the next part, it says, given that the skydiver eventually descends safely to the ground at a constant speed of 6 meters per second, evaluate the model. For this part, as the skydiver descends, its speed eventually becomes a constant speed of 6. So as it descends, the speed of the parachute, we want it to eventually become a constant value. But let's see what the model tells us. For large values of t, we want to see if the speed eventually becomes a constant value. So as the skydiver descending, when t becomes large, so when t becomes infinitely large, let's say, we know that e to the power of minus 0.5t will essentially become 0. And to see why that is, e to the power of t goes to infinite. E to the power of minus t is the same as 1 over e to the power of t, which becomes 1 over infinite, and anything divided by infinite obviously is going to reach 0. So e to the power negative 0.5t becomes 0. And if you look at here, if this becomes 0, then the 0 times 50.1 is also going to be 0. Therefore, v will eventually reach 5.89, which is equal to 6 if we round it to 1 SF. So therefore, we can say that the model is appropriate. So the model does give us a constant speed of v equal to 6 for large t values, which is basically what is observed by the skydiver where he eventually descends to the ground at 6 meters per second. So we can say that the model is valid. Question 10. This modulus question, I mean, it can be easy or it can be hard. It depends on how they design the question in the final exam. First part of the question is just asking you to sketch the modulus graph. The second part, or should we say part C, where you have to work out the range of values for g of x given by this, is a little bit tricky. So first part, question A, sketch the modulus graph given. So if you look at what's inside the modulus graph, it's 3 times x minus 2a. So in order to see what's happening to the graph, what happens to the original graph, which is the modulus of x, let me just write this out first. So modulus of 3x minus 2a. So this is basically, this is essentially the transformation of the graph of y equals modulus of x. So if we have a coordinate axis, if we sketch the graph of y equals modulus x, so modulus x is something like this. So that's the y equals modulus x, where the lowest point has coordinate 0, 0. So this is y equals modulus x. Now, if you look at the equation given here, it's the 3 here that's kind of in the way. So, I mean, if you were to sketch this as it is, you would have to follow the reverse of the order of operation in order to transform the graph. But in order to, I mean, going backwards and going forward, it all depends on how it's written. Best way to do this would be to factorize the 3 out the modulus sign. So y equals to 3 bracket, and then divide everything inside by 3, gives you x minus 2a over 3. And then we can just follow our normal rule of transformation. If you now look inside the bracket, because we're subtracting off 2a over 3, the graph will shift to the right by 2a over 3 along the x-axis. And on the y-axis, obviously, it's just going to be multiplied by 3. So it's a stretch of factor of 3 along the y-axis. So if we now sketch this modulus graph, so the original modulus graph will have shifted 2a over 3 to the right. And because there's no numbers on the y-axis, it doesn't really matter with the scale factor of 3. So we can just do a v like this. And on the x-axis, so this would be 2a over 3, 0 for the coordinate where it intercepts the x-axis, because we are asked to state the coordinates of each point where the graph cuts or meets the coordinate axis. And then the next one we need to give is where it crosses the y-axis. Obviously, that's where x equals 0. So if you substitute in x equals 0 into the function, we get y as modulus of minus 2a, which is the same as 2a. So this is 0, 2a on the y-axis. There you go. So this is the graph of y equals modulus of 3x minus 2a. And if you can see that if we didn't take the 3 out, then we just have to do the reverse of BIDMAS. We'll have to shift it by 2a to the right and then divide all the x values by 3. And by doing so, we get the same answer. Or take the 3 out and then just shift it to the right by 2a over 3. All right, question B, solve the equation given. Okay, so question part B, the modulus of 3x minus 2a is less than or equal to x plus a. So there's two versions to this equation. So if we do the positive version of that equation, we would get 3x minus 2a is less than or equal to x plus a, or 2x is less than or equal to 3a, or x is less than or equal to 3a over 2. And if we do the negative version of that equation, which is basically minus bracket 3x minus 2a is less than or equal to x plus a, or minus 3x plus 2a is less than or equal to x plus a. A is less than or equal to 4x, or a quarter of a is less than or equal to x, which basically means the same as saying x is more than or equal to a quarter of a. So what does this all mean? So there's essentially two range of values. X is either less than or equal to 3/2 of a, or x is more than a quarter of a. So it looks like, it's a closed interval. There's more than a quarter of a and less than 3/2 of a. So that kind of forms a closed interval. So from this, we can say that x is less than or equal to 3/2 of a, but more than or equal to a quarter of a. Now, question C, given that the modulus of 3x minus 2a is less than a, if that's given, that kind of implies that the domain of g of x has to satisfy the solution we got from part B of this question, which is x has to be less than equal to 3/2 of a, but more than equal to a quarter of a. So this part here, where x has to be where this has to be satisfied, tells us the domain of the function of g of x. So this is essentially our domain, and it says find in terms of a the range of the possible values of g of x, where g of x is given there. So let's just copy this formula. Right, so to answer this question, I'm gonna sketch the graph, because it'd be easier to explain this by sketching the graph, and then looking at how the graph behaves when the two extreme of the domain goes into the function. So that's a quarter of a and 3/2 of a. When those two values get substituted into the g of x, we want to see what kind of output values we get in terms of a. And then if you have a look on the graph, we can actually see, if on the y-axis, if it goes any higher or any lower. So y equals modulus. I'm going to start from basics. So y equals modulus x again, just like what we did in the first part of the question. So this is y equals mod x. One thing to note is that the modulus of 1/2 a minus x is actually the same as the modulus of x minus 1/2 of a. Because if you swap them around, this introduces a negative value. So that's the same as negative of x minus 1/2 a. And what the modulus does is it removes the negative, so that gives you the same as what we have above, which is x minus 1/2 of a. So this basically means the same as that, which means the graph just shifts a half a to the right. So if we now shift this a half a to the right, we'll get a graph something like this. So here is a half of a. What we have then is a negative sign outside the modulus graph. So if we now want to draw the graph of y equals negative modulus x minus a half of a, the negative, because negative is outside the bracket, is going to affect the y values. All the y values are going to be multiplied by -1. So essentially, all the y values will flip on the x-axis, i.e. it's going to reflect on the x-axis. So the reflection of the graph will now, so we just have to flip the graph now on the x-axis. So the v graph will now be like this. So this is the graph of the y equals negative of modulus of x minus a half a. And if you now go back, g of x equals to 5a minus the modulus of a half a minus x, which is basically the same as minus modulus x minus a half a plus 5a. So having the plus 5a attached to it, obviously because it's outside the bracket, it means all the y values are going to go up by 5a. So you just have to move the graph up by 5a. So if I just do one more sketch of the axes, right? So our v graph will now just go up, go high up, and it will reach here. So this value here is a half of a, but the highest point is now going to be 5a because it goes up by 5a. Now the y-intercept of this graph, well, we may or may not need the y-intercept. Let's go to the domain of the function again. The domain of the function is between so less than equal to 3/2 of a, but more than equal to 1/4 of a. So we can see that this is half a, so 3/2 of a would be somewhere here. So let's say that's 3/2a, and 1/4 of a would be somewhere here, so that's 1/4 of a. So if we were to substitute in 1/4 of a into the g of x function, that will take us across an upper value there, and 3/2 of a will take us across and to the left somewhere there. So to work out those values, you just have to sub those input values into the g of x function. So if we substitute in 1/4 of a into g of x, this will give us 5a minus modulus of half a minus 1/4 of a. So that's 5a minus modulus of 1/4 minus a half minus 1/4 is 1/4. So we don't really need the modulus sign here. So 5 minus 1/4 is 4 3/4. So if I zoom in, so this would be 4 3/4 of a. And if we substitute in 3/2a into g of x, so that's 5a minus and a half minus 3/2 is equal to minus a. So that's the same as 5a take away a. So that gives us 4a. So this is equal to 4a. So if we now look at the graph, the lowest output we get is 4a, which is here, and the highest is all the way up to 5a. Not 3/4, not 4 3/4 of a, it goes all the way up to the highest point, which is 5a. So from that we can see that g of x is therefore going to be less than equal to 5a, but more than equal to 4a. Now, obviously, I've gone through this in a lot more detail than required, but at least you can see the steps needed to get to the range of a function. If you can sketch it, you can see we can see the highest point it reaches on the y-axis, so you get the upper limit straight away. And to get the lower limits, you just have to substitute the values of the two extremes of the domain into the function of g of x. That's a quarter a and 3/2 of a. So which one gives you the lowest y value, and that becomes the lower point of your range. Right, in this question we're asked to rearrange or simplify the expression on the left hand side, show that it becomes tan theta. I'm going to write tan theta as sine theta over cos theta, so that at least we can see that if we can get the left side into this side, into sine over cos, then we can get the tan theta out. Now, by looking at the expression on the left, we can see that we got sine 2 theta and we got cos 2 theta, whereas on the right side it's just a single angle theta. So that's a hint that we have to use double angle formulas. The numerator is sine 2 theta, so we can replace sine 2 theta with 2 sine theta cos theta, because there's one version of the double angle for sine, plus sine theta. Now on the denominator we have cos 2 theta. There's 3 versions for cos 2 theta. Which version do we pick? Well, this is where this comes in. On the denominator we only want coses to remain, so that's a hint that we're going to use the cos version for this one. So cos theta, we're going to replace that with 2 cos squared theta minus 1. Then we have plus cos theta plus 1. So we can knock off the ones here. And now we're going to factorize out the sine theta from the top. So we're left with 2 cos theta plus 1. And if we do the same underneath, factorize out the cos theta from the denominator, you have 2 cos theta plus 1. And you can see that this bracket cancels this bracket off. We get sine over cos, which becomes our tan theta. Now, question B, we asked to hence or otherwise solve the equation given here. Now, if we look at this equation and look at this equation, more or less the same expression. So if we were to say theta equals to x, then this is essentially the same as that, because you can see that theta is x, so 2 theta will give us 2x. So if theta is equal to x, then this expression here therefore can be written as tan. So it becomes tan x. So tan of x is equal to 2 cos x. Tan theta, we can change that into, or tan x equals to sine x over cos x equals to 2 times cos x. Take the cos x to the other side. So take the cos x to the right side and multiply. So that gives us sine x equals to 2 cos squared x. Now we've got two different trig functions in this equation. We can't factorize the sine or the cos out, in which case in order to get a single trig function, we're going to have to replace the cos squared with 1 minus sine squared theta. So that expands into 2 minus 2 sine squared theta. So that rearranges to 2 sine squared theta plus sine x minus 2 equals to 0. And if we now factorize this quadratic, so we can see that it's going to be, I think it will factorize. Right, so it won't factorize, so let's just use the quadratic formula or the calculator. Right, so we get sine theta equals to -1 plus root. Okay, so just realized that we can't really use this method here. Just notice here that solutions relying entirely on calculator technology are not acceptable. So in order to solve this quadratic, we're going to have to resort to other methods. Okay, I take it back. You can actually use the quadratic formula here. This bit here where it says no solutions relying entirely on calculator not being acceptable is where you can just draw the graph on the graphical calculator and just read off the solution. That's not allowed here. So we're not obviously entirely using the calculator because most of it was done without the calculator. So we're just going to use it for the quadratic part. So this gives us sine theta equals to -1 plus root 17 over 4, and the second one is sine theta equals to -1 minus root 17 over 4. This one as a decimal is -1.28, which means that it's more than, or it's less than -1. So this one will have no solutions because sine obviously can only go as low as -1. All right, so sine x equals -1 plus root 17 over 4 is valid. Right, for now this sine inverse on this expression, we get 0.896 to 3 decimal places. Now using the cast diagram, our sine is positive here and it's positive here. So this angle here is 0.896, so is this one here. Given that the original x value is between 0 and pi, first one we get to is the 0.896, so the second solution would be all the way here. So the next one would be pi minus 0.896, and this gives us x equal to 2.246 to 3 decimal places. You might be wondering, if we use this value and do 2 minus this value here, you don't get 2.246. What I've done was I used the original value in the calculator. I did pi minus that. So to reduce rounding error, you need to use more digits. So we need to actually use the original value of the sine inverse that you received. Right, so a kettle contains a quantity of water. Water is cooling down. The temperature theta of the water at time t minutes after cooling began is modeled by this equation given here, where A and K are constants to be determined. So the temperature theta equals to 21 plus A e to the power of minus K times T. So the first bullet point tells us that at the instant cooling began, so when T equals to 0, the temperature theta equals to 80, and 40 minutes after cooling began, and you can note that T is in minutes. When T equals to 40, the temperature theta was equal to 33 degrees Celsius. Find the complete equation of the model giving the exact value of A and the value of K to 3 significant figures, because A has to be exact. Okay, so if you substitute the first bullet point, so when T equals to 0, theta equals to 80 into this equation here, we get 80 equals to 21 plus A e to the power of 0, and e to the power of 0 is 1, so we can just get rid of that. So that kind of gives us A is 80 minus 21, which is equal to 59. If you now substitute the second set of values, t equals to 40, theta equals to 33 into the function. Right, so substituting t equals 40 and theta equals 33 into the equation gives us 33 equals to 21 plus a, which we have as 59 e to the power of minus 40 times k, because t equals 40. So to subtract 31 from 33, that gives us 12 equals to 59 e to the minus 40 times k, or e to the minus 40k equals to 12 over 59, and take ln to both sides, so minus 40k equals to ln of 12 over 59, so that kind of gives us k equals to minus 1 over 40 ln of 12 over 59, or if we now put that into a calculator and round k to 3 significant figures, right, so that gives us k as 0.0398 to 3 significant figures. So therefore the complete equation for theta equals to 21 plus 59 e to the power of minus 0.0398 t. Question B. Given that 20 minutes after cooling began, the temperature of the water was 48 degrees Celsius, evaluate the model. So we can see that t is measured in minutes. So for question B, we're going to substitute in t as 20, and we're going to measure, or we're going to work out what theta is. So 21 plus 59 e to the power of minus 0.0398 times by 20. We put that into our calculator and see what happens. Gives us 47.616 dot dot dot. So we can see that this is approximately equal to 48, rounded to 2 significant figures. So therefore we can say that the model is appropriate, as 47.6 is approximately equal to 48. Right, and part C, according to the model, the rate of the decrease in temperature of the water 20 minutes after cooling began. Well, the rate of change of theta is basically given as d theta by dt. It's the differentiation with respect to t, and that's the same as rate of change. So if you now differentiate our theta, 21 goes away. Just a quick reminder, if theta equals to 21 plus 59 e to the power of minus kt, then d theta by dt will equal to 21 goes away, so we get 59 times by minus k e to the power of minus kt, and k obviously is minus 0.0398, so this would be minus 59 times by 0.0398 e to the power of minus 0.0398 t. And we want to find the rate of change when when t is how many minutes? 20 minutes after cooling began. So substitute t as 20 into that. So d by dt equals, just substitute that into a calculator, we get a value of minus 1.06 degrees Celsius. So therefore it's decreasing at a rate of 1.06 degrees Celsius per minute. Integrate x squared e to the power of x to the power 3 with respect to x. Now, when you look at it at first, you see a product of two functions. So your first instinct will probably be to start using the integration by parts. But if you look closely enough, you can see that the derivative of the power of e to the x, a multiple of that is actually sitting at the front of our exponential. So this essentially is the reverse chain rule method for integration. If you still can't see the reverse chain rule, then we can apply a substitution for this one. So if we say u equals to x to the power 3, then this integration becomes x squared e to the power of u. And then if we differentiate du by dx, which gives us 3x squared, so dx is essentially du over 3x squared. Substitute this in for the dx, so this will be times by du over 3x squared. So the x squared cancels off, so we get the integration of a third of e to the u du, which is basically a third of e to the u, plus c, your constant. Now put the u back in, so that gives you a third of e to the power of x cubed plus c, and that's the integration done. Hence it's just reverse general. So if we were to use the reverse general formula on this, the integration, so same thing again, but just doing the reverse general method. So what differentiate, so we can see that the derivative of x cubed is sitting at the front, so we're going to try the same function e to the x cubed, and if you differentiate that, we get 3x squared e to the power of x cubed, and to adjust that we need to multiply by 1/3, so this essentially is 1/3 of e to the x cubed plus c, which is the answer that we got here as well. Now if we were to do this, if we were to try to do this using the integration by parts, you'll probably get to a point where you can't integrate this function. So just quickly show you, if you were to use by parts, what happens here. So x squared e to the x cubed dx. So if we make this u and make this v dash, you see that u equals to x squared, u dash equals to 2x, v dash equals to e to the x cubed, and then in order to get v we have to integrate e to the x cubed, and that's where things will get problematic, because we can't really integrate this using our normal conventional methods. So reverse general. Okay, so question B, use substitution. So we're going to use u as x to the power 3, so du by dx equals to 3x squared, which means dx equals to du over 3x squared. So substitute in for the obvious one first, so I'm going to keep my x to the power of 8 for now, even though we can replace it. And then we have e to the power of x cubed, which becomes e to the power of u, times dx, which is du over 3x squared. So simplify here, so we have a third of x to the power of, so if we now subtract the powers, your power of 8 minus 2 is power of 6, x power 6, and then e to the power of u du. If we now go back to our substitution, u equals to x to the power 3. So if we were to square this, this would be squared, which gives us x to the power of 6. So x to the power 6 is basically our u squared. So it becomes 1/3 of u squared e to the power u du. Now, in order to integrate this, I believe we have to use integration by parts now. So this can't be reverse general, because if we differentiate e to the u, we get e to the u, we don't get the u squared. So we're going to use integration by parts for this one. So this will be one, using u's and using u's again for integration by parts is going to get a little bit confusing here. So what we can do is, well, we're going to have to use different letters for our u and v dash, or we can just switch back into x and then just switch it back to something else afterwards. I'm gonna just do it in different color. So integration of 1 over 3. I'm just gonna switch the u back into an x, e to the x du, so that we can use this as u, and this would be our v dash. Otherwise it'd be confusing using u's everywhere. So u equals to a third of x squared, so u dash would be 2 over 3x. V dash equals to e to the x, so v equals to e to the x, because e to the x integrates back into e to the x. So by parts formula, uv minus integration of u dash v, so that's u times v gives us a third of x squared e to the x minus integration of u dash v. So u dash is this times by v, which is this. So if we multiply them together, we're going to get 2/3 out of that. So I'm going to put the 2/3 outside the bracket, or sorry, outside the integral. So we get 2/3 of x e to the power of x. And you probably notice that we now have to do by parts again on this bit. So I'm just going to put that aside. So we're going to do integration of x e to the x now with respect to x. So u equals to x now, u dash equals to 1, v dash equals to e to the x, so v equals to e to the x. Again, that's the uv minus integration of u dash v. So u times v is x e to the x minus integration of u dash v is just e to the x. So that is x e to the x minus e to the x, and then I'm going to put plus constant. I'm not going to put plus constant c in just yet. So this will go back into here, and we're going to write the final answer, well, not the final one, the expression for this final for this bit. That is a third x squared e to the power x minus 2/3. Minus 2/3 times everything that we got down below. So it'll be minus 2/3 of x e to the x, and then minus 2/3 times another minus gives you a plus 2/3 of e to the x. And now we're going to put plus c in, because I mean, I don't need to multiply the c with the minus 2/3. It's a constant, so just overall constant could be just our plus c. Now comes the issue of this one here. The fact that we switched it into an x, we now need to switch it back into a u. So this is basically 1/3 of u squared e to the u minus 2/3 of u e to the u plus 2/3 of e to the u plus c. Now we're gonna switch the u, which is x cubed. I'm gonna put that back into here, or put that into there. So we now have 1/3 of u squared, so that's going to be x to the power 6 e to the power of x cubed minus 2/3 of x to the power 3 e to the power of x cubed plus 2/3 of e to the power of x cubed plus c. If we look above, it looks like they have factorized out 1/3 of e to the power x cubed. So if we do the same, take out 1/3 of e to the power of x cubed. So we'll be left with x to the power 6 minus 2 x to the power 3 plus 2, because e to the power x cubed has been, 1/3 of e to the power x cubed has been taken out. Close that, and then plus c. We compare this to what we have above. So it looks like, if we compare these, it looks like a is the coefficient of x cubed, and then it's a constant. So a therefore equals to minus 2, and b equals to 2. Double check that. Question A, express this as a partial fraction. So because the denominator is already factorized, 1 over x bracket 100 minus x, we can write this as a over x plus b over 100 minus x. So this means if we now multiply everything, both sides, with x bracket 100 minus x, then 1 is therefore equals to a times 100 minus x plus b times by x. So if we just substitute in for x's, so x equals 0 gives us 1 equals to 100a. So a therefore equals to 1 over 100. And if x equals to 100, that gives us 1 equals to 100b, which means b is also equal to 1 over 100. So therefore the partial fraction we're looking for, let's do it underneath here, is equal to 1 over 100x plus 1 over 100 bracket 100 minus x. Okay, part B. A scientist is studying the spread of fungus in a field. The field has an area of 100 meters squared. The area of the field affected by the fungus, x meters squared, is modeled by this differential equation. Alright, so for part B, the differential equation that we need to solve is 500 dx by dt equals to x bracket 100 minus x. But t days is the time after the start of the study. So when t equals to 0, x equals to 5. Solve the differential equation to show that x is equal to this formula given here. Right, so in order to solve this, we need to separate the variables. So we're going to take the dt to this side and multiply, and we're going to take all of that to the left hand side and divide it across. So if we do that step, we're going to get 500 over x bracket 100 minus x dx equals to dt. Now if we scroll up and look at our partial fraction, we see that this fraction here and this fraction are very similar, but we need this to be 1. So in that case, I'm going to divide across by 500, so we want that to be a 1 here. If we divide both sides by 500, we get 1 over x bracket 100 minus x dx equals to 1 over 500 times dt. And now we can put the integration sign on both sides. This now matches the partial fraction we had in part A, so we can just replace that with the partial fraction. So this is the same as 1 over 100 x plus 1 over 100 bracket 100 minus x dx equals to 1 over 500 dt, or the integration of that. Alright, so integrate this. Well, this will give us, well, before we integrate, I'm just going to rewrite this as, I'm going to just cross out the 100 from here and just do 1 over 100 like this. This is 1 over 100, and then you can see that this is basically the ln. So this would be 1 over 100 times ln of x, and then it would be plus 1 over 100, and then it will be the ln of 100 minus x, but because of the minus x inside, it's going to be a negative 1 ln of 100 minus x. And on the right side, it'll be 1 over 500 times t plus our constant. And to work out what that constant is, t0 x equals 5. Substitute in t equals 0 and x equals to 5 into this. So we get 1 over 100 ln 5 minus 1 over 100 ln of 100 minus 5 is 95 equals to 0 plus c. So that's what c is. So 1 over 100, factorize that out, and it'll be ln 5 minus ln 95, which is basically the same as ln of 5 over 95 equals c. And simplify that. So that's 1 over 100 ln of 1 over 19, which is the same as ln 1 minus ln 19, ln 1 being 0, or minus 1 over 100 ln of 19. It's just simplified it into a slowest form, lowest term. So now this is now 1 over 100 ln x minus 1 over 100 ln of 100 minus x equals to 1 over 500 t minus 1 over 100 ln of 19. I guess we need to make x a subject. To make x a subject, we're going to multiply everything by 100 to get rid of all the 1 over 100s. So multiply both sides by 100. So we'll have ln x minus ln of 100 minus x equals to 1 over 5t minus ln of 19. I'm going to take that to the left hand side and add it onto the left hand side. So we'll have ln x minus ln of 100 minus x plus ln of 19 equals to 1/5 of t. Then use the laws of logarithms. Ln a minus ln b will be ln of a over b plus ln c, which would multiply. So what we now have would be a single ln would be 19x over 100 minus x equals to 1/5 of t. So e both sides, so we get 19x over 100 minus x equals to e to the power of 1/5 of t. Now we need to take that bracket to the right and expand this out. So 19x will be equal to 100 e to the power of 1/5 of t minus x e to the power of 1/5 of t. We need to make x a subject, so we're going to take that to the left hand side and add it on to the 19x. So 19x plus x e to the power of 1/5 t equals to 100 e to the 1/5 t. Factorize the x out of both terms and then divide across by the bracket. Okay, and now just have a look above. It looks like the final answer here, there's only an e. The factor of e is just on the denominator, and it's a -5th. There's no e's anywhere else. So to get that version of the answer, we're going to have to divide everything on the top and the bottom by e to the power of 1/5 of t. So by doing this, we now have x equals to 100 over, so it'll be 19 divided by e to the power of 1/5 of t. So I think that's meant to be e to the power of, when to say e to the power of 1/5 of t. So 1/5 of t plus 1. So that's the same as saying x equals to 100 over 1 plus 19 e to the power of minus 1/5 of t. So therefore a equals to 100 and b equals to 19. C, hence find the area affected by the fungus 10 days after the start of the study. So question C, 10 days. So substitute in t equals to 10. So x would be 100 over 1 plus 10. Oh, it's 1 plus 19 e to the power of minus 1 over 5 times 10. So just sub this all into your calculator. So that gives you 28 meters squared for the area. Question 14. Figure 1 shows a sketch of a curve with parametric equations x equals to a half theta times sine theta and y equals to 1/3 of sec theta, and theta is between 0 and 5 pi by 12. So that's the domain value for theta given. Point P lies on the curve where theta equals pi by 3. So point P, which is here, so at this point we know that the theta value equals to pi by 3, and we're asked to find in the simplest form the exact coordinate of point P. Well, the exact coordinate or coordinate point P will be x comma y, and we just have to substitute in our theta value into the equation for x and y to work out the coordinates for y, and just to make sure that we are given the answers in exact form. So if it's in third or in terms of pi, we have to leave it in terms of thirds and pi, just to make sure that it's simplified. Okay, so for question part A, just doing that little space here. So question A, at point P, we know that theta equals to pi by 3. So substitute that into the x coordinate. So we have a half times by theta, which is pi by 3, times by sine of pi by 3. And if we just plug that into a calculator and simplify, well, we'll simplify it for us, we should get root 3 over 12 times by pi. Right, and we now substitute the theta value into the y equation. So y equals to 1/3 of sec. So sec theta is 1 over cos, so it'll be 1/3 times by 1 over cos. So it'll be 1 over cos of pi by 3. So if you substitute this into your calculator, you'll get the y as 2 over 3. So therefore, the coordinate of point P equals to, the x coordinate is root 3 over 12 pi times by, comma, and y coordinate is 2/3. So we have the coordinate of point P. I'm just going to annotate that onto the diagram. So point P, if we drop down from point P on the x-axis, so the x value here is root 3 over 12 times pi. And at the same time, if we go across from point P along towards the left, we can see that we'll meet the y-axis at 2/3. So now we're ready to move on to part B of the question. Line L meets the curve at point P and is parallel to the x-axis. So because L is parallel to the x-axis and we know that L intersects the y-axis at 2/3, I mean, we have the equation of line L is going to be y equals to 2/3. But anyway, let's move on. The region R shown shaded is bounded by the curve, the y-axis, and the line. Show that the area of the region R is given by this expression here. Okay, so I'm just going to make note of this. We're going to work out the area of region R. Right? Show bit, obviously, we're going to show how we get to the answer. So let's just say, how would you work out the area of region R? So let me just take a snapshot of that integration and move on to another page for more space. Let's start off by looking at the area of that region. So the area of region R will be equal to the area. If you look at it, it's the area underneath line L. And because line L is horizontal, the area underneath line L would be the area of a rectangle. So if we draw a rectangle just to illustrate that part, so this rectangle will have a base of root 3 over 12 times pi and a height of 2/3. So with the area of the rectangle, and then if we now look at the area underneath the curve, right? So the area underneath the curve is this white region here. So the area underneath the curve will be given as the integration from x equals to 0 to x, so 0 is here, to x equals to root 3 over 12 pi of y dx. So that's the integration given in Cartesian form. So to work out the area underneath the curve, we just integrate the y with respect to x. And we minus that from the rectangle, giving you the area of region R. So that's how you would initially write down the area of region R is the area of a rectangle minus the area underneath the curve given, obviously. Just express it in Cartesian form for now. So this bit here is the area underneath the curve C given in Cartesian form. And as the equation of curve C is given parametrically, we're going to have to adjust the integration and use the parametric integration form. So to do that, well, let's just work out the area of our rectangle first. That's the easy part. So area of rectangle would be root 3 over 12 pi times by 2 over 3. And if we work this out, so this will be 1 over 6. So it'll be 1 over 18 times pi times root 3. So that's the area of our rectangle. Now the integration part, we're going to integrate. So instead of Cartesian, switching to parametric, because the equations are given in terms of theta, it's going to be y times dx by d theta times by d theta is switching to parametric form. That's the parametric form for area underneath the curve. And these have to be the theta values corresponding to the x values given above. And from the equation given above, we can see that when x equals to 0, theta has to be equal to 0, because if theta is 0 here, it will make the whole expression equal to 0. And we already have the next one as well. When x equals to root 3 over 12 pi, that's basically at point P, and we're given that at point P, theta is pi by 3. So here we can just take theta as pi by 3. So going back to our integration, the bottom would be 0 and the top limit would be pi by 3. Okay, the y part of the integration is basically 1/3 of sec. We can just substitute that in. And then the dx d theta we can get by differentiating the x part. So let's just start with the differentiation of x. Now x equals to a half theta times sine theta, and we need to differentiate the x with respect to theta. And if you look at the function for x, it has two variables. It's a product of two functions, so we have to use the product rule for differentiation here. So make the half theta our u and the sine theta our v. Then if you differentiate uv, you would get u dash v plus u v dash. Or if you prefer writing them out separately, we have u equals to a half theta, so u dash would be a half. You have v equals to sine theta, so v dash would be cos theta. And then if you put that into the product rule, formula for the product rule, we get u dash times by v, so that is going to give us a half sine theta plus uv dash, which will give us a half theta cos theta. If we now substitute all of that into our integration, so the integration therefore will be between 0 and pi by 3 of y, which is 1/3 of sec theta. So that's 1/3 times sec theta multiplied by dx d theta, which is a half times sine theta plus a half theta cos theta d theta. Now, if we multiply out, so if we multiply the sec or the third sec into the bracket, it will get, so 1/3 times 1/2 is 1/6, 1/6, and we'll get sine theta times by sec theta plus we get another 1/6 theta times by cos theta times by sec theta, all of that, and then we got a d theta and 0 and pi by 3 there. Now, sec remember is 1/cos. Just ready to make a note here. So sine theta times sec theta, sine theta times 1/cos theta, and sine times 1/cos becomes our tan theta. And so sine times sec is tan, and cos times sec, well, sec is 1/cos again, and 1/cos times cos is just 1. So this integration will now simplify to 0 and pi by 3 of 1/6 times tan theta plus 1/6 theta d theta, and we can factorize out the 1/6. So this will leave us with tan theta plus theta d theta. So now if we put all of them together, so therefore area of region R is equal to the area of the rectangle, which is 1/18 times pi root 3 minus the area underneath the curve given by the integration of 1/6 from 0 to pi by 3 of tan theta plus theta d theta, and that's, I believe, what we had to show. If we go back up, yep, there we go. So A is the coefficient of the area at the front, and B is the coefficient multiplying the integration. So in that case, our A equals to 1/18, and our B equals to, is it positive or negative? So minus, so B is positive 1/6 because the form above already has a negative in the expression. Right, part C, hence use algebraic integration to find the exact area of R. The integration part, so we want to integrate, so part C, integration from 0 to pi by 3 of tan theta plus theta d theta. Now the integration of tan theta, you can look this up on the formula booklet. This is ln of sec theta. So this, we can go straight into the answer for this one for integration. So tan, the integration of tan is ln of sec theta. Integration of theta, we just use the year 1 integration raised by a power. So it will be theta to the power of 2, and then divided by 2 or multiplied by half, 0 and pi by 3. So we have 1/6. Let's keep the 1/6 outside. Substitute in pi by 3. So this would be ln of sec of pi by 3. So 1/cos pi by 3 plus 1/2 of theta squared. So that's going to be pi squared over 9. So that's what we get when we substitute in pi by 3 minus, round bracket, now 0 goes in, so this would be ln of 1/cos of 0 minus 1/2 times 0 squared, and then close the brackets. Cos of this obviously is going to be 0, cos of 0 is 1, 1 over 1 is 1, so this is 1, and ln 1 is 0, so all that also goes away. And if you simplify what's inside the ln, that gives you 2. So if we now put all that together, so we have 1 over 6 times by ln of 2 plus 1 over 108 pi squared. So that's the area underneath the curve. So the area of region R would be 1 over 18 pi root 3 minus 1 over 6 ln to minus 1 over 108 pi squared would be the exact area of region R.